In the previous video, we looked at a simple linear regression model. So explaining variation in a response variable y based on observations of the predictor variable x. And we explained this with that the y value would be the alpha plus beta times the associated x value, but that each of those model points, it's not going to explain it perfectly. There will be some residual error, some difference between what this simple straight line model is saying and what was actually observed. We define the residual error as being the distance between what the model would have predicted with this straight line in this case and the actual data point observed for the y at that x value. Now, intuitively, if I've got two models and one has got very large residuals, so the line is a long way away from what was actually observed, and I have another model where the residuals are much smaller, fairly obviously we would think that a model with smaller residuals is, in general, a better model. The most common way to fit a model to estimate the coefficients is what we call ordinary least squares. So this is choosing our estimates of the intercept alpha and the slope beta such that we minimize the sum of squared residuals, hence the least squares. Now there's two advantages to working off this squaring of residuals. Well, obviously positive and negative residuals of the same size, of the same magnitude, are treated equally. And it also really strongly penalizes where the model is a long way from the observation, because being twice as far away gives you 4 times the squared residual. Being 3 times as far away gives you 9 times as large a squared residual. I suppose it arguably has a third benefit, which is that the other option that people sometimes use is looking at just the absolute value of the distances. But differentiating an absolute value is a lot harder than differentiating to optimize a squared term. So let's start from our two constraints here. We said that, well, if we included an intercept term, the expectation of the residuals being 0 means that the sum of the residual errors should be 0. So if I work out the sum of the residuals, then I get some constraint on this, on what I can choose for alpha and beta, or the estimates of them. So when I rearrange this, then what I will get to is I'll get the sum of the yi observations minus n alpha minus the sum of beta times the x's has to be 0. And a simple rearrangement of that gives me that alpha should be the sum of the yi's minus the sum of beta times xi over n. I suppose I should have said that alpha hat an estimate of alpha. So that when I work this out, then I can say that alpha hat is y bar minus beta x bar, where x bar and y bar are just the sort of sample averages, the average of the xi's that was observed and the average of the yi's that was observed. Now the other part's a little bit harder, because what I need to do is I need to find which value of beta minimizes the sum of the squared errors. Now obviously I can't set this to 0 because it will in general not be that, but I just want to minimize it. So the way that we would minimize this is by differentiation, finding the turning point. Before we differentiate to find the turning point of these squared residuals, there's a couple of nice mathematical, tricks which I want to implement. Well, I know the estimate of the intercept term alpha hat, which is y bar minus beta x bar, so I'll put that term in. I can then regroup this just as yi minus y bar minus beta xi minus x bar all squared. And that's the difference of two squares within the sum. So I can rewrite it as the first term squared plus the last term squared minus twice the product of the two terms, the xi minus x bar and the yi minus y bar. So if I then differentiate this, well, my first term doesn't depend on beta at all, so it vanishes. My middle term is just minus 2 beta lots of it, so I'll get minus 2 lots of it. And then the back term, the beta squared lots of xi minus x bar, will just give me 2 beta xi minus x bar squared. And setting that to 0, I can then rearrange it to get that the beta value that would come out of this would be my estimate, beta hat being the sum of xi minus x bar times yi minus y bar divided by the sum of xi minus x bar squared. Let's actually apply this to a data set, and again, a data set which measures exactly what I totally made up. So here is a set of observations of x and observations of the response y. I think fairly clearly we can see that the trend line will go top left to bottom right, so a negative gradient. It drops between about, say, an intercept term of about 7 and a slope it goes down from x is 0, y is about 6 or 7 to x is about 10, y is about 2. So it drops about 5 units as it goes across 10 vertically. So it has a slope of about minus 0.5, I believe. But I don't want to do this based on I believe. I want to do this a little bit more rigorously. Well, the sum of the integers 0 to 10 is 55. And the sum of the yi's, you can check it or you can trust me if you wish to, sum to 38.5. This gives me an x bar of 5. There's 11 observations that sum to 55, so an average of 5. And there's 11 observations of y, which sum to 38.5, giving y bar of 3.5. If I now put in two more columns to this table, the xi minus x bar and the yi minus y bar, how much above or below the mean of its variable is each observation? So when I sum the xi minus x bar column all squared, well, I've got minus 5 squared plus minus 4 squared plus minus 3 squared, and so on. And that sums to 110. And if I take the product of the last two columns, so minus 5 lots of 2.1, minus 4 lots of 2, minus 3 lots of 2.4, then I'm claiming that that sums to minus 47.9. So when I put all of that together, what I obtain is beta hat being this minus 47.9, the sum of the xi minus x bars, multiplied by the yi minus y bars, divided by the sum of the xi minus x bar squared. So this gives me a slope of approximately minus 0.436. And I said, from eyeballing it, I expected about minus a half, and then I can substitute through, and I'll get an intercept term of, I guessed about 6, and it's a little bit below that. So the simple linear regression model we get is something like that. I think I've probably drawn the line a little bit high there, but that's roughly what I'm expecting. A simple linear regression model doesn't necessarily mean that it's a linear relationship between the terms. Like, for example, I could fit a quadratic relationship whereby yi is alpha plus beta xi squared plus some residual error. I could fit that by simple linear regression if I regarded x squared as my predictor. Because it would still be a straight line if I plotted y against x squared. So I can include nonlinear terms, provided I treat however I put those terms in linearly. So if I plot y against x squared for this quadratic model, I would still get a straight line. The other thing to note is that to this point, we've not made any assumption about the distribution of the residuals. It's often said that you need the residuals to be independent and need them to be normally distributed with constant variance. That actually isn't true. We haven't actually assumed that at any point. Where some of the confusion lies is that some further analyses that are done on a regression model do require some distributional assumptions, but just simple ordinary least squares, there's absolutely no assumption about the distribution of the residuals.